Welcome to Calculus Chat, a weekly discussion with your lecturers for 114. I'm Dr. Biggs, and here with me is Dr. Kellerman
Hello.
and Professor van der Walt.
Hello.
I think that was another good, busy week. Lots of learning and lots of action happening.
Yeah, the Discord server was on fire.
Yes, I wasn't there that much this week. I had too many other things to deal with. Um, what did we do? Let's start with maybe the tutorials, right? We were working on the next worksheet, really getting into the limit. And I think, from the question I have is that we're still getting to grips with the writing of the language of mathematics. And sometimes I also try and explain to students that it's a bit like learning a language. You can't just expect to read and then suddenly be fluent in writing. You have to practice it. You have to speak to fluent speakers so that you can get better at it.
Yeah, absolutely. And it is a bit of a strange language because, unlike the natural languages that we speak from a day to day basis, English and Zulu and Hungarian and Afrikaans and whatever, it's a very formal and a very precise language. And this takes getting used to, but it takes practice.
Mhm.
Yeah, it's a science and an art. It's like a computer programming language. It has an exact syntax. If you change a bracket or a semicolon, the computer will not understand what you're saying. You have to be exact with mathematics, but it's also a skill that you can improve in the art of concise but accurate mathematical communication. And you learn that skill by doing things like reading good mathematics books, but also yourself practicing writing out proofs.
And I think I some years ago when I was teaching a third year analysis course where things are even more precise and finicky than they are now in 114, I told my students that this precise way of expressing yourself, which is so important in mathematics, I think it is a really valuable skill even beyond
Oh,
mathematics. And
yes.
if you're not going to become a mathematician, then you're probably never going to be asked to calculate a limit. But the ability to reason in a very precise and rigorous way is an invaluable skill for whatever you're going to do one day.
Very good point. Yeah, no, I mean, I think if I just look at some people I've known, if you have those skills, have that training in mathematics. It's the deeper skills that you get by getting that training that makes you so valuable. And most of the people I've known have almost just immediately gotten jobs. Often, I mean, in various industries, but it's that skill is in high demand.
Yes, if you have a mathematics qualification, it witnesses the fact that you have probably a well trained mind. You know how to reason analytically, and that is definitely a skill that is in high demand.
And I also like the point of that there's a bit of an art to it. There's a bit of creativity, right? And so we often get the students asking, and this week particularly, I had quite a few of these. Is well, how do you start a proof, or how do you go about finding a counterexample? And well, there is no algorithm. There is no magic way. That's why we can't just do mathematics by giving it to a computer.
Yeah.
We have to have the creativity of humans involved.
Yes, but I think there are still some general sort of principles that you can apply. And the first thing is to just identify what exactly do I have to prove,
Yeah.
and what is given. What do I know, and what are the tools that I have in my mathematical toolbox that relate to the things that are given. So if you want to prove something, about these limits, like we had in the worksheet. Well, okay, what's given? This limit is this limit is that. What are my tools? I've got the limit laws. Which one can I use?
No, I mean that's half the battle already won.
Yeah, very often, once you've identified what to prove very carefully, and once you've written down what you know very carefully, then the proof is kind of obvious.
Yeah, then it's not so hard to see how to connect those 2 points.
Yeah.
It's also important to know your definitions. I find many students don't know their definitions, but definitions and proofs are to the mathematician what the rules of soccer are to a soccer player, or the rules of rugby to a rugby player. A rugby player can't run around on the field and have to look up the rules while he's playing. He needs to know them so that in the heat of the moment he knows what he can and cannot do. If you know what you can and cannot do, because you know your definitions and theorems, then it's much easier. But if you don't know your definitions and theorems, then you're going to have a problem if you have to keep looking them up.
In the middle of the field with your little book. That's a beautiful analogy.
Excellent. It's an excellent analogy.
And I mean, speaking of definitions, what also came up in some of the previous worksheets is sometimes, or in statements, is that uh, we find that they are not precise enough. But this is exactly how mathematics develops, and
Mm.
how we actually form definitions. Is we see that, well, actually there's some ambiguity around this term. It doesn't fully capture the idea we want to capture precisely, and well, then we reformulate the definition and make it more precise. So on the other hand, the point I'm trying to make is that definitions are also living things. They're not
Mm.
set in stone there, that is the definition. That they are a definition we make in order to do something. And if we find that there's some problems, well, then we can go and fiddle sometimes with the definition.
Yeah, I mean, there's this kind of joke. Old theorems never die; they become definitions.
Yes, I
And
love that one.
yeah, and that's precisely what happens. You start off working with it and you prove a bunch of theorems, and then eventually you realize exactly how you're supposed to define the thing you want to be working with. Only after having sort of played with the thing for a long time.
Mhm. And I mean, so the one example that comes to mind is the what our students have been battling with a little bit is the increasing decreasing, because they might
Mm.
have seen the definition in terms of the derivative of a function being positive or negative, and then it's increasing or decreasing at that point. And now we've thrown another definition at them for what does increasing and decreasing mean. So we're starting from a different point of view, and we're going to come back and we're going to connect it to that idea of the derivative. But that for us is going to be a theorem. It's going to be a result.
Yeah, and but you see, and that's a very good example because that definition of increasing, saying the derivative is positive, is actually, it turns out, really not a good definition.
Yes.
There's an example of a function on the interval 0, 1 into the real numbers, a continuous function. It is differentiable almost everywhere, and the derivative is 0 whenever it exists, but the function is strictly increasing.
Yeah.
This is a mind-blowing example.
Yes.
And it shows that defining increasing in terms of the derivative is a very bad idea.
Yeah. But I mean, it's okay if you're talking about functions that are everywhere differentiable and smooth. But as soon as you want to go and play in a bit of a bigger arena, you need to generalize that definition.
Well, even for differentiable functions, I mean, you can have a function that's strictly increasing, but its derivative is 0 at a point, and then it kind of
Yeah.
makes you a little bit uncomfortable.
Yeah, I mean, even there's so would you say something like x cubed is strictly increasing everywhere? Well, if you have the definition by the derivative, you'd say no, because at zero, derivative is zero. But actually, I mean, if you're talking about, well, what is at the essence of increasing, surely x cubed must be increasing everywhere.
Yeah.
So I think our students are, I think some of them at least, slowly starting to find their feet and seeing what this game of mathematics is about, and learning how to express themselves. But I also think some of our students are starting to realize, whoa, the water is a little bit deeper than we thought. There's more depth to this. It's not quite just, oh, increasing, decreasing, odd, even. Yeah, we know this stuff. It will be easy.
Mm.
I would say it reminds me of the samurai saying the boat rises with the tide if the water is deeper than the students thought. As mathematics gets harder, one also gets better at it, so ultimately it is possible to rise to the occasion.
Yes, but unlike a boat rising with the tide, this takes some serious effort. Right? The boat plays no role in its rising. The water picks it up. Learning mathematics, on the other hand, rising with the mathematical tide, you're going to have to do some serious pedaling to get to the top.
Indeed. And I mean, some of these, well, coming back to definitions again, they might feel a little laborious. Like, why are we spending so much time and effort to talk about something simple like increasing? Of course, we can see what we mean by increasing.
Mm,
Like, why do we have to develop all of this so very carefully? And I think that is at the heart of what we're trying to do here is we're trying to really build the theory slowly from the
mm,
ground up. And to do that, we have to be very careful to have strong foundations so that we are in
yeah,
100% agreement and can make good statements.
mm. Well, I think it speaks to the nature of mathematics. At its heart, mathematics is a deductive axiomatic science.
Yeah,
Yeah, mathematics isn't based on a physical reality. It's abstract. So if you take something like a topological space, there's no good, compelling physical reason why the axioms are what they are. And so if you speak of an open set or a closed set, people who don't know topology might be surprised to learn that a set can be both open and closed. So the moral of the story is you shouldn't read too much into the terminology. The terminology is often suggestive of what intuitively the object does, but if you speak of an increasing function, you have to make it mathematically precise to avoid ambiguity because it's an abstract concept.
indeed. Okay, so what did we do in this week's lectures? So we solidly on our way to completing theme two, right, on limits and continuity. I think we managed to do the nice squeeze sandwich theorem for limits, which is actually I think it's quite a nifty little theorem. It allows you to do some pretty extraordinary things.
Yeah, there's lots of examples that you simply can't handle without it, or which, if you were to try to handle without it, it becomes really messy. The squeeze theorem is a great tool in mathematics, in calculus, and in analysis beyond that. It's a fantastic result.
And then we got going on continuity.
Yeah, we talked a lot about continuity in the lecture videos. They besides being kind of the basic objects for calculus, they also provide additional tools for evaluating limits. We've got a nice composition theorem. Yeah, well, I'm quite a fan of continuous functions. It's one of my main research interests.
I believe next week we continue off with finishing a few things. And one of the big results that I very much like from first year is the intermediate value theorem, right, for
Ooh,
continuous functions. And it's such a simple idea that if we sort of connect 2 points, we have to move through all the points in between them.
yes. And it's in fact such a natural thing to think that should be true when you're talking about continuous functions, that historically people kind of included this in the definition of continuity. They thought that satisfying the conclusion of the intermediate value theorem and continuity is kind of the same thing.
Uh huh.
Right? But there's a nice surprise for you. Right? This is not the case. Very counterintuitive.
And I mean, it's also one of the theorems that I think you can start basing very simple numerical algorithms on, namely the bisection method, right? If you have a continuous function at the heart of an equation, there's a very simple and easy way of trying to find a root for that function, which is you just keep on cutting it.
Yes, that's actually quite surprising. It's a simple idea, and it leads to actually quite a powerful numerical method. I mean, your error decreases exponentially, which is quite impressive for a numerical method.
Well, there are faster methods.
Yeah.
I think one of the amazing things about it is just how stable it is.
Mm,
It is really reliable, and I think often the numerical algorithms use that as a starting point.
yeah.
And then only when they get closer to a good approximation do they sometimes switch over to an even faster way of approaching that route.
Yeah, well, I mean, yes, it is not the fastest method around, but it is extremely general
Yeah,
in that you have relatively weak assumptions. You're only assuming continuity of the function defining your equation, whereas some of your faster methods, like Newton-Raphson, for instance, requires much stronger assumptions on the function, differentiability, and that the derivative is bounded; it's not too big.
and you kind of have to start close enough, otherwise very bad things can happen.
Yes, no, this bisection method is actually quite remarkable.
Yes, and as students will see this week when we start looking at differentiation, every differentiable function is continuous. So one of the reasons why continuity is a mathematically important property is because your class of differentiable functions is a subclass of the class of continuous functions. And of course, differentiation is one of the main concepts in calculus.
Yeah, so that is a result which we are going to prove quite carefully
Mm.
using our good knowledge that we've built up for limits.
Yes, but that is, speaking of proving this carefully, that's another thing about the intermediate value theorem that is quite, strange. Is that, okay, there's a lot of things that we haven't proven so far. So we didn't prove any
Yes.
of the limit laws and things like that, but we already have all the mathematical tools we need to prove everything we've discussed so far. There's nothing that we cannot prove except the intermediate value theorem. This theorem, for its proof, requires you to go much deeper into the foundations of analysis, into trying to understand exactly what is this thing that we call the real line.
Yes, and it's a topic, of course, that we return to in later years. In second year, we do dig into. We spend some considerable of time answering the question, what is a real number? And we need that background in order to actually prove the intermediate value theorem,
Yep.
because that's the depth that is needed to get
Mm.
into it. And in a way, it's kind of surprising that there's so much depth there in such an intuitive and simple seeming theorem.
Yeah, that tells you it's a deep result.
Yeah. And well, at this point, I always start liking to think about the philosophical question of, well, is the universe continuous? So many objects in reality have long thought to be sort of continuous, infinitely divisible. But then as time goes by, well, no, then we discover actually there is a smallest part in some sense. And I guess that has definitely been applied to matter in many places,
Mm.
but hasn't sort of been applied to space and time. And there's a bit of a question, well, is space and time infinitely divisible?
This is a very interesting question. Well, I was at a physics conference a couple of years ago in Sweden, really nice place to visit. But there, somebody gave a talk and they had developed a discrete model for space time consisting of a lattice of quantum gates.
Jeepers.
Yeah, so basically, this is a computer science idea. This gate, like that you have in classical computer science, but that's
Mm-hmm.
binary. You have to 0, 1, 0, 1. Quantum gates are kind of continuous in the sense that you don't have just 0 and 1. That was very interesting. So I don't know if it's right, if it's the ultimate correct model of the universe, but it was quite amusing that somebody thought of this thing and that it kind of agreed with observation to some extent.
Are you referring, Rory, to the Planck length and Planck time as, in a sense, the smallest distance and period of time that can be described using classical physics?
So yes, we already classical physics is discovering there's some limitations to what we can observe, right? But the sort of the fundamental nature, I'm still not sure whether there's an answer to that. Whether it is by nature actually continuous, whether or whether if a particle is moving through space, does it jump in quantum
Ah,
bits?
Yes, also the observable universe is basically finite, and from the standpoint of constructing abstract objects, that means there are many things that can't really be constructed. For example, you can approximate pi using finitely many decimals, but because of the finite nature of our observable universe, you can never store the infinitely many decimals of pi. So pi is a mathematical abstraction that can't necessarily be realized in our physical universe. And I guess if space and time are discrete rather than continuous, then curiously the real numbers are also a mathematical abstraction to describe the physical universe that we live in.
And one that has been remarkably effective
mm,
uh, in describing it.
yes. Well, we're getting into some deep philosophical questions here about the existence of mathematical objects.
Indeed.
I've always found it curious that the three dimensions of space, you have freedom of movement, but time you can only move forward. I've always found that to be an oddity.
Hmm.
Well, before we go off completely on a tangent, um, our next theme, right, which we start next week, is, well, around tangents.
Yeah, speaking of
And I mean, you could say that the idea of a tangent line, which I believe we've already introduced with the limit and talking about the problem of finding the tangent line, is sort of quite central to calculus. And it's this idea of sort of trying to approximate a rather complicated object with something much simpler and easier to deal with, a line. And this gets generalized as you go further in maths into well a higher dimensional linear object. It's a really powerful idea.
Yes, I mean it's fundamental in many parts of mathematics and its applications to physics. I mean, in differential equations, which we use to model things in physics, biology, chemistry, everywhere, very often you're dealing with a nonlinear equation, but you can approximate it linearly, locally, and this very often gives you very good results. It simplifies your problems quite a lot.
So yeah, next week we start then to the good job of carefully building that up from the foundation and from the definition. And then next week, of course, I think what will definitely be on our students' mind is, of course, the big semester test, right? And the role of the semester test is, well, it's sort of summative in nature. It's to see, well, have our students internalized and mastered the topics that we have done so far. Also, well, we don't pause for the semester test, right? Lectures are going to continue going on, and we're going to continue facing new topics. So this is quite a lot to handle, but it is part of what university life is is to handle all of that. But if you have been keeping up to date, right, and you have been studying and completing all the worksheets and studying for your tutorial tests, then it doesn't have to be a very big thing that you need to study for, because then you have already mastered that material.
Yes, absolutely. I mean, I say, and I'm borrowing a phrase from our head of department, Professor Angelov, that you don't start studying for the semester test, 5 days before the semester test or the exam. You start studying for it the first day of semester. Every worksheet you do, the videos you watch, the exercises you try, you're preparing.
Yeah, so by this time, you should actually have already fully studied for the semester test. We've covered all the work for it. We've covered all the worksheets that are covered in it. We've had 2 tests on it.
Yeah. Now it's just the time to look back on the things that we've done and say, okay, well, here was something I didn't understand. Let me go back and look at it again. You shouldn't be looking at something for the first time now. Then you're in trouble.
Yeah, my previous piano teacher used to call it Thursday evening rush jobs, when one prepares on a Thursday evening for your Friday session. You need more time than one evening.
So, is there any advice that we'd like to give our students going into their semester test? And it probably could be one of their first semester tests at university.
Well, one thing I can tell you, don't pull an all-nighter the night before the semester test. Make sure you got a good night's sleep, you're rested. Otherwise, I mean, you may now have studied, I hadn't gotten an extra, 8 hours of studying in, but I mean, you're going to be so tired, it's just going to be gone.
And you're going to make all kinds of nonsensical, silly mistakes. We speak from experience.
Personal experience.
Yes, no, there is nothing quite as important for a healthy mind as a good night's sleep.
Yes.
Anything else to add?
Well, look, I think it's important that when you're writing your test, take when you get the thing, go through it, read it, identify the questions. And, okay, that one I know, this one I know, and get going.
Yeah, I used to sort of in my mind tell myself a little story when I started the test, which was, now is the time to relax. The hard part is over. There's nothing more I can do to go and study. I've done all the hard work of studying and mastering the material. What I don't know now. And there's nothing I can do about it. Now I get to relax and I get to communicate what I know. And there's really not too much I can do about now suddenly fixing something that I have a hole in or not fixing it. So relax, write that test, and communicate what you know and put your best foot forward.
Yeah, another very important thing, I think, and I've seen this so many times. Read the question carefully. Don't scan the question for where's the key word that's going to tell me what to do. Read every word of the question, because so often a student comes after the test has been graded, and I say, well, no, just read the question out loud. word for word. And then it's like a, oh, okay, now I know.
Indeed. Yeah, and I mean, as you read the question, after you've read it one time, then you read it again and you start unpacking, right? What are those definitions? What is it that you're trying to show?
Mm.
And as we said, well, usually then half the battle is already won. Okay, well, I think that's going to be it for this time. So, all the best with your semester test, and do make sure you get a few nights of good sleep before that. Uh, until then, cheers.
Bye.
Goodbye, and good luck also with your other semester test in your other modules.
Ciao.